Hello everyone. During the 8th International Renewable and Sustainable Energy Conference, I'm going to present my work Untitled, Pressure, Size, Impurity, and the Internal Composition Effects on Shallow Donor Bending Energy in InGaN, Square, Simple and Double Quantum Well. In this presentation, the bending energy of a hydrogenic shallow donor impurity in simple and double quantum wells based on unstrained wurtzite InGaN are investigated. Considering the effective mass and dielectric mismatch between the well and its surrounding matrix, the numerical calculations are performed within the framework of the parabolic band and the single band effective mass approximations under the finite potential barrier using the finite element method. In this study, we used the structures in Figure 1 of a simple quantum well and a double quantum well. The results are given in the effective units. The effective readback energy as the unit of the energy, and the effective bore radius as the unit of length. The form used in our calculations of the Hamiltonian is given in equation 1. To study the pressure effect, we took into account in our calculations the dependence of other parameters of the pressure and the indium concentration. The parameters are the barrier potential, the band gap energy, dielectric constant, effective mass, and the well barrier width. The eigenvalues of the given Hamiltonian can be obtained with a numerical method using the finite element method. The ground state bending energy is obtained as the difference between the ground state energy in the absence of impurity and the ground state energy in the presence of impurity. To be sure of our calculations, first we plotted in Figure 2 the finite square well heterostructure showing the potential profile and the first three density probabilities, which is in a good agreement with the previous works. In Figure 3, we plotted the potential barrier as a function of a hydrostatic pressure for three Indium fractions. We can see that the potential barrier increases with the increase in pressure. Also, for a fixed value of pressure, we can see that the effect of the indium concentration. And with the increase in indium fraction, the potential barrier increases. In Figure 4, we plotted the ground state bending energy in InGaN simple quantum well as a function of the well width for three values of the pressure. First, we can see that the bending energy decreases versus the well width for finally to converge to the bulk limit. As the well width diminishes, the wave function starts to feel the presence of the potential barrier and its 3D character goes to 2D behavior, which leads to an increase of the bending energy. And we can see that there is a maximum for a critical value of the well width. Also, for the pressure effect, we can see that the increase in pressure increases the bending energy. In the Figure 5, we plotted the ground state bending energy in InGaN double quantum well as a function of the well width for the three values of the pressure. First, we can see that the bending energy shows its maximum for a critical value of a well width. Also, for the pressure effect, when the pressure increases, the bending energy increases also. So, as a conclusion, the shallow donor impurity ground state bending energy in InGaN quantum well is investigated numerically within the effective mass approximation. The pressure dependency of the band gap, the well barrier length, the effective mass, and the potential barrier reveals that the shallow donor bending energy first increases non-linearly as a function of the hydrostatic pressure. Second, presents a maximum corresponding to a certain critical value of the length. Third, is strongly sensitive to the internal parameters and can be adjusted by the quantum well barrier width, the impurity position, and the internal indium composition. So, our results are in a good agreement with the finding, especially for those obtained by the variational approach.